Geoffrey Taylor of Oxford University conducted some experiments to show kinematic reversibility of low Reynolds number flows. The following film illustrates this effect.
Low Reynolds number flows are reversible when the direction of motion of the boundaries which gave rise to the flow is reversed. This may lead to some surprising situations which might almost make one believe that the fluid has a memory of its own. Here are two concentric cylinders. The fluid can be moved by turning the inner cylinder with this handle. The annulus between them is filled with glycerine. Into this space I introduce some dye which stays put owing to the high viscosity of the glycerine. Note its position before I start turning it. I now turn it 4 times, pushing the handle clockwise. The dye seems to mix as a drop of milk mixes when it is stirred into a cup of tea. Now I reverse the direction. And after turning exactly 4 turns, the dyed area reappears in its original position, with a little fuzziness due to molecular diffusion.
In this picture, we saw that the rotation of the inner cylinder causes organized motion with the fluid layers sliding over one another. We have seen earlier that the motion in low Reynolds number flow is quasi-steady. This implies that time does not matter. The pattern of motion is the same whether slow or fast, forward or backward in time. Thus, the blob in the first figure becomes oblong in the second figure. It becomes part of a spiral in the third figure. And then we reverse the flow and we go through the stages, and finally we acquire the same blob shape, except for a little diffusion that might have taken place during this time. The distance traveled by each layer decreases in the direction of increasing radius, and therefore the blob acquires a spiral shape as shown. The dyed glycerin molecules spread out, but not randomly, the diffusion being too slow. On reversing the motion of the inner cylinder, the fluid layers slide back and reassemble as the blob. In low Reynolds number flow, we can extinguish a candle by suction if we could extinguish it by blowing. It is another matter that we cannot blow out such a candle. But if we could also suck it out because the motion is reversible. This cannot happen in the case of high Reynolds number flow, where it is easy to blow out a candle, but you can't suck it out. Kinematic reversibility is a direct consequence of the linearity of the governing equation in its steady form. The flow everywhere depends linearly on the instantaneous boundary conditions. If the velocity at the boundaries are reversed, the velocities are reversed everywhere, and so is the pressure. It's easy to demonstrate the kinematic reversibility by a deck of cards on the side of which we have painted this picture, and when we slide this deck, it acquires the shape. If we apply a force in the reverse direction to slide, we can get back the same. This very roughly gives you an idea of kinematic reversibility. Let us now talk of the falling bodies. We have talked of the terminal velocity, which is the velocity that a body acquires under the action of its own wet weight and the drag in the fluid it is moving. The Stokes equation gave the drag as 6 pi r mu v. For a sphere. But the interesting thing is that this drag does not depend upon the shape of the body. This graph here shows that at low Reynolds number less than 1, all points for 6 different types of bodies: sphere, ellipsoid shaped particles, cube shaped particles, and cylinder shaped particles, and frustum shaped particles have all the same drag coefficient. So it's quite independent of the shape of the body at very low Reynolds number. Of course, as the Reynolds number increases, this particle deviate from the line for the spherical particles. Since the weight of the particle varies like r cube and the drag on it varies like radius times the velocity, from the equation the drag is like 6 pi r mu v. The terminal velocity in this creeping flow limit varies like r square. The larger particle travels much faster than smaller particles. If the diameter of the particle is twice that of a smaller particle, then its terminal speed would be 4 times. This is seen in the fact that a terminal velocity of 2.5 micrometer dust particles, which cause a lot of air pollution, is about 1.5 into 10 to the minus 3 meters per second, 1.5 millimeter per second. While there are 10 micrometer particles, 4 times the diameter, the terminal speed is 2.4 centimeters per second compared to 1.5 millimeters per second. The effect of the presence of bead creeping down a fluid column is felt over a large distance. Because of this, the motion of beads far away from a moving bead are affected by its motion. The presence of nearby wall affects the motion of the beads. This happens only in low Reynolds number flow. It will not happen in high Reynolds number flow. Of the 2 beads, one close to a wall and the other far away, the bead close to the wall moves slower because of the presence of the wall. As a consequence of the kinematic reversibility, the bead travels at a constant distance from the wall. The effects referred to above have been demonstrated very well by Jeffrey Taylor in the same movie that we referred to above.
The drag of a falling sphere is proportional to its diameter and to its speed. The net weight of the sphere is proportional to the cube of its diameter. The velocity is therefore proportional to d squared. They have diameters in the ratio of 2 to 1, so that the larger one falls in syrup 4 times as fast as the smaller. At low Reynolds numbers, the disturbance produced by a moving ball extends many diameters, so that beads far from the ball are moved by its passing. Thus, the presence of a nearby wall can be important. Here are 2 identical balls, one near a wall and one far from it. The ball near the wall falls more slowly. Incidentally, it remains at a constant distance from the wall, a consequence of reversibility. This retarding effect also slows the fall of a particle surrounded by many similar ones, so that a cloud of them falls more slowly than a single one. When a cloud of assorted particles falls in a fluid, it develops a sharply defined top. A particle which has a terminal velocity rather lower than its neighbours doesn't always get left behind. If it did, it would find itself isolated and would fall faster and therefore catch up the rest.
Thank you very much.